Welcome, students, to Week 1 Synchronous session for Physics B. I am your instructor, Mr. Sharan. So this is, for many of you, this may be your first time hearing my voice or meeting me. So welcome to my class, and welcome to our first synchronous session. Now, this is not just for the people who showed up to the original synchronous session itself, but this is for all the students who are tuning into the asynchronous version of this, where you're watching a recording of this session and will be following along for this. Just a little things about the synchronous sessions before we begin. These are being held once a week on Tuesdays at 3 p.m. for your course. If you're unable to make those, that's fine. I will be posting either a recording of the session or an alternate assignment for you, which you will see in the course announcements portion of your course itself. So if you go to course announcements, you should see these posted there once a week. Now, each of these, currently at the moment, I am writing follow-up assessments for these. So for each one of these assignments, there is a sheet which I'll be providing for you. You should be able to see the sheet there on the screen. I have it centered on the screen at the moment. And also you will be provided with links to a simulator to do this. I prefer to do, instead of lecture, online labs, and lab demonstrations, as I find that's a better way to kind of get across science than just pure lecture and note taking. So, as you follow along, do make sure that you have the lab sheet with you so you can fill this out as you go, and it will help you when you do the follow-up quiz afterwards. So, for week 1, I wanted to take a moment to do some refresher on periodic motion, specifically waves in rope or waves in string. Now, waves in particular, since we're going to be covering sound and light as part of the current first 2 units, are going to be very important concepts for us to understand. So this refresher is designed for that purpose. So let me read through this. Follow along as I go. So waves in the rope simulation. Aim of this activity: to observe relationships between frequency, wavelength, speed of waves in a rope, and observe how these change with changing the tension in a rope. So we've got a couple of key terms here: frequency, wavelength, speed of wave. So so all three of those together are related together in a equation, which we're going to derive and talk about as part of this lesson, and also tension. So if we identify some of our key terms, frequency, wavelength, speed of wave, and tension are all going to be part of those. Now to do this, you'll be going to the Waves on the String applet app, which can be found at the following website. I will also have a link for this in the course announcement, but you can click on the sheet itself to do that. In fact, let me open that up. Now, to get you to see what that looks like when loaded, this is what it shall look like. So this will be what your initial activity will look like. Now, we are going to be using this, but I'm going to jump back and forth between screens because I want us to be able to see for sure what's going on the rest. Okay, so we got waves in a rope simulation. As part of this, we're first going to be taking a look in our first experiment on the speed of wave and tension. So we're going to be looking at the relationship to a wave speed and its tension. So we're going to set the experiment to pulse, fixed N. We're going to set the dampening to none, normal tension, normal, and then tension, normal speed, so this is the speed, and tension low. And we also want to turn the ruler and timer on. So, pulse, none, normal, and what else do we need? And tension low. So we're going to start with low tension. Now, low tension here is... So low tension would represent a loose wire or a loose rope. Now we are currently using the fixed end setting, So we are in the fixed end setting. So just to give you an idea of what that looks like, this is the fixed end setting. This is the loose end setting, and this is the no end setting. Okay? Now, all three of those we're going to see have an effect on what happened to the pulse or the wave in the string once it reaches this other end. So we're going to see how that affects that here. So now, going back to our instructions, we're looking at a couple of different things, okay? So at low tension, so I'm going to do the low tension portion myself, and then you guys will be responsible for completing the medium and high and making your conclusions from that. So let's start with the low. So we're going to be doing time for pulse to travel 5 lengths, time to travel 1 length, distance to travel 1 length, and speed of wave, which is equal to the distance over the time. So let's take a look at this first one. So we should also get our ruler, and we should have our timers. Ruler, I'm going to set it to here. This is actually perfect. And then timer. Now, here's a little thing we should do. Before you ever start, pause it. What this allows you to do is click buttons, but nothing will occur until you unpause it. So, oops, actually, I guess that was not 100% true. Shouldn't have done that. Alright, so let me reset that actually. Okay, so fixed end, pulse, ruler timer, normal, no dampening, low tension. Alright, pause it. I'm going to set the turn on the stopwatch. So as soon as I hit the pulse button, it's going to start running the time. So it'll be perfectly timed up. And a loose fixed end, if I'm missing normal. Alright. I'm going to leave these as is. Amplitude, pulse wave, I'm going to leave them all as is. So we'll get a fairly even setting. Alright, so let's just see. So the first thing we're looking for, once again, just to remind you, time for pulse to travel 5 lengths. Okay, so 5 lengths is once and back is 2 lengths. So it's got to go all the way to one end, all the way back, all the way to one end, all the way back, and then all the way to that end again, and that'll be time for 5 lengths. So let's see how long that takes. All right. So 1, 2, 3, 4, 5. Okay, so there's a little bit of discrepancy, but I get about 30.47 seconds. So I'm going to type that in here. Notice I include my unit, whenever possible, S for seconds. All right, so let's see how long it takes to travel 1 length. Now this might be a little trickier for us to do, so I'm going to reset again. Pulse, dampening, ruler timer. I like that there. Pause, set it up. All right, so I just want to see how long it takes for the pulse here to reach there. All right. Okay, so little harder for me to see. In fact, I'd say I sort of messed that one up, so I'm going to reset it. So as you do this is something you'll notice, and this is really true of any experiment. They almost never run right the first time you do them. So you usually have to do more than one trial. This is why multiple trials are usually used. I want to make sure I get this right, so I'm going to click to slow-mo. This will actually slow the whole simulator down, but still will accurately measure the real-time time. Alright, so let's go again. Alright. right. So, all right. So that took about 1.5 seconds. Oh, you know what? Made another mistake. Forgot to turn on my dampening. So I got to make sure that was all to 0. So we'll do this one more time. Once again, I'm going to kick slow mo. The simulator asks you to use normal, but it's really fast, so I want to be able to see it. And all right. Okay, so we're going to try this again one more time. Oh, turn the dampening all the way up. All right, try this one more time. All right, as you're seeing, we're getting a lot. Oops, getting a lot of error here. So let's make sure everything's now set right. All right, there we go. A little easier to see. Okay, so I probably overshot a little, but I got about 1.44, so I'm going to record that. All right. Now, distance traveled in one length. So this one a little easier to conduct. This is where our ruler is going to come in. So we're going from measurement to measurement. So I've got 7.1. Now, see, 1, 2, 3, 4, 5. So this is so zero point 0.2, 0.4, 0.6. So 7.6 and centimeters. All right, so let's get that down. 7.6 centimeters. And now I need to know the speed. So I can do this a couple of different ways. Let's take a look at the first way that we can conduct this. So the first way is pretty straightforward. I can take the distance traveled and divide it by the travel time and get an answer. So I'm taking 7.6, and I'm going to divide that by, um, 7.6, and I'm going to divide by, here we go, oops, hang on, I'm trying to get my calculator to show up on the screen. All right, so I'm going to do 7.6 divided by 1.44. All right, so 7.6 divided by 1.44, I get roughly 5.28. Although if I take a look at my numbers, I only have two significant figures. 2 here, 3 here. I always go with the lower of the two, so I should actually 5.3 centimeters per second. Okay. Now, what we want to see, the next thing is, we'll reconstruct this again. We're going to see how is this affect the calculations as we increase the tension. So just to go over what it could do, what could potentially be the consequences or outcomes of it, you could either have that it increases the velocity or speed, it decreases, or it just stays the same. So all three are viable, but it's going to only be one. So you'll use this value here. All right. Now, just to see, just to kind of let you see how that looks, just take a look at that here. So same setup once again. Low tension. Oops, did I have it set to high tension? Uh-oh. Yep, I had it set incorrectly. All right, let's reset this. Yeah, I did. I had it set to high. So those numbers, let me just switch those down. All right, I'm going to put these over here. All right. Okay, so actually, we those are the numbers for high tension. So let's see what happens with low tension. Low tension. Oh, rulers and stopwatch. All right, pause here. Low tension, all else set. Go. All right, so we see the wave reaching it. It took about 6 seconds. So if I were to go here, distance traveled for one length. Took about, not about, actually, it took exactly 6.07. And distance travel is not changing. So we still have a value here to look for, and we still need to do the center. But just looking at our starting pattern, it definitely seems to be when you have lower tension, it takes longer for the same sort of pulse of energy to travel to the string. So we should see that as part of our patterns. Okay, let's go on to the next portion. So once again, you'll finish out the rest of this to answer your questions about the conclusion here. All right, so let's go from there. Okay, so we're going to go back. This time we're going to set to oscillate. So that means instead of doing a pulse, it'll do continuing and no end. So let's go back. Oscillate, no end. I'm going to leave everything else as is. Um, let's see, what else do we need to do? We're going to set the frequency to 1 and tension to low. Measure the time it takes for the wave to travel the length of the string. Measure the length of a single wavelength. Do the frequent Do the same for measure for frequency equal to 2 and 3. Repeat the experiment at moderate and high tension. So let's take a look at our board. So I'm going to do, at frequency 1, I'm going to do low, moderate, high tension. Show you how to do it. You'll do the rest as part of your experiment. All right, so let's take a look at this. So let's start with the first one. So I want low tension, no dampening. What else do we need? And let's do the frequency. So we want frequency to be 1. All right. And I'm going to do set to slow again because I want to see, because if you notice what time travel, time to travel, length of string. So we want just one length. And then we're going to look at the wavelength. Um, and we're going to see what frequency times wavelength gives us. So we've got frequency 1. All right, now. All right. Okay, so with no end on the other end, there's no reflection of the wave. So this wave creates what we refer to as a standing wave. What you're seeing here is a standing wave. Now, there's a couple of things that we wanted to measure. One of them, I can't do because I forgot to set it to the timer on. But let's get the other measurements. So we were looking at the time to travel the length of the string. I'll have to come back to that. But I can record the wavelength. So at this low tension, so wavelength is very simply, we want the distance from trough to trough. Okay. So in this case, we're looking at about, let's see, max here. All right, so I'm looking at 1.2, sitting around in the center, so I'm going to 1.25. So for my wavelength, 1.25 centimeters. Okay. We need the travel time, which I'm going to need to get again. So I'm going to reset this real quick. Oscillate. Stop. No end. All right, pause this. Oscillate. Ruler's timer. Ruler timer. All right. Okay. Turn on. No dampening. Frequency down to 1. Missing anything? Oh, we did low tension. And once again, I'm going to set it to slow-mo so I can see, oh, and no end. So I'm looking to see how long it takes to get to the other end. So this green dot here, basically when it moves, I'll pause. All right, almost there. All right, so a little over, but 6.14. All right, so speed, I've got centimeters per second. So, all right, so we've got 1.25. Oops. So 1.25 divided by 6.14. All right, so we've got a speed of 0.2 centimeters per second. We're going to have to see how that goes with the frequency and the wavelength. So let's take a look at our frequency. Frequency is 1 hertz. All right, so 1 hertz is 1 over seconds. So it's basically a oscillation per second. What that means, and then for every oscillation per second, we're going to multiply it by its wavelength. Oops, I did the speed wrong. Caught an error. Remember, the length of the string we said was 7.6. I actually should have a different velocity here. Okay, so 7.6 divided by 6.14, it gives us a little better. 1.24 centimeters per second. Sorry, should have been the length of the string. Length of string. All right, and then I'm going to compare that to the frequency of the wavelength. If I multiply the frequency of 1 hertz, which is 1 over s, 1 with 1 over s as the unit, and the wavelength, which is 1.25, oops, 0.25 centimeter per second. All right, so very close. So I got very close between the two. So which easily could be explained away by experimental error, specifically reaction time. So let's take a look at it again and moderate. So I'm going to reset again. No end. Pause. Oscillate. Let's get this down to 1. Let's do medium tension. Ruler's timer. Turn the timer on. All right, so we're going to do the same thing again. So this time I want to see, oops, slow motion. How long does it take for this to move? That would be our 7 point, give us the same length. And then we'll take our measurements from there. All right. So, oh, I noticed an error. I had an error again. As you can see, oh yeah, stop that. No end. Oscillate. Let's get this down to 1. No dampening. Medium tension. Timer. Ruler. All right, this time I should have it. Slow-mo. Should have. Hopefully you're seeing how this could be a bit of a problem if you're not paying attention. All right. So that took about 2.08 seconds. So travel time at moderate for frequency of run, 2.08 seconds. Wavelength, let's take a look at what the wavelength is. So this is where the first trough is going to be. Actually, I'm going to measure it this way. So from here to about here, so I've got 3, 3.2, 3.4, 3.6, 3.8, 6, 8. This is 3.7. So I would say halfway between would be 3.7. So it almost looks like 3.75 if I were to really get it down there. So 3.75 centimeters. Let's take a look at the speed now. So the speed, so once again we're going with our 7.6. So it's a 7.6. This time divided by 2.08. And I get 3.65 centimeters per second. If I multiply the wavelength, 3.75, and the frequency of 1, I get 3.75 centimeters per second. Oops, centimeters per second. So once again, still a bit of a discrepancy, a larger discrepancy here. So this is more likely, I would say this is probably more likely due to either my timing value was too much. In fact, actually, let's try that real quick. 7.6. 3.8. So I might actually. It looks like I might have stopped it too soon. 7.6. Yeah, I probably stopped a little too soon on this one, and my wavelength's probably a little off. So we want to double check those, but we should see that we're getting a pretty similar pattern. All right, one more to try. I'm gonna start one more time. Okay, same frequency 1. This time we're gonna do high tension. Now we're gonna see how long. Oops, slow motion. How long this takes. All right. So as you can see, this one's a lot longer, the wavelength. I would say if we're measuring it wavelength to wavelength, we're looking at roughly 6 point. Oh, what does that look like to you? I'd say 6.2. Okay, so I'm going to say So we're looking at high tension, 6.2 centimeters. Our wavelength is, oh, sorry, our time was 1.29. And we will do our calculations here. So we've got our, once again, 7.6 centimeters divided by 1.29, 0.89, oops, sorry, second. If I take the wavelength and I multiply it by the frequency, I get centimeters per second. All right. Oops. Let's just make sure. Yep. No tension. All right. So we're getting a little bit of discrepancy in our experiment, which is expected. That's what we refer to as experimental error. But we are seeing a pattern emerging that, at the very least, as our tension changes, our wave speed seems to change as well. Specifically, as tension increases, so does the speed of the wave. Now, we'll need to confirm this by also seeing how the changing the frequency affects it as well. But if this pattern holds, we should see some pretty straightforwards. Okay. Now, what we should get out of this. So let's take a look at a couple of questions as a follow-up to this. So if the tension remains constant and the frequency increases, what happens to the wavelength? Okay, so tension doesn't change. If frequency increases, what happens to the wavelength? So as you complete your experiment, you should see that answer. Is there any pattern to the last two columns of the table? All right. Well, if we're just seeing what we have, the pattern that we seem to see is that the speed of the wave seems to be very close, if not equal, to the frequency of the wave times the wave's actual length. And then finally, what is the relationship between frequency, wave, and the speed of the wave? So this is where we'll derive a final equation where speed of the wave is equal to, and in this case we've already really kind of confirmed it, frequency times wavelength. So now, like I said, I haven't gone through all of this with you. I've only done parts of this because it's up to you to complete the rest of this. You should be able to, though, answer the conclusion questions. After you've done your lab and you've watched the video and done this lab and filled out this table with these questions, do make sure to go back to the course announcement and do the follow-up assessment that comes with this assignment. So that's it for us today. If you have any questions, please feel free to contact me on this. You can contact me directly through the system or by email. But I hope everyone has a nice rest of their day, and I hope this was helpful in sort of reinforcing some of the things we know about waves.